The next method I'm going to talk about is the open loop bump method. Now this is the method we're going to use, and it's really quite involved. I'll be honest with you, it's quite involved. After you've done a couple of hundred of these, you'll find that you're doing them real quick, and you're not even thinking about it. But the first couple you do, they do seem a little bit complicated. So I'm going to go through this nice and slowly, I hope, and I hope that you can follow along with me. Right. Here are the results from a flow bump. Now, those of you that have got books, you'll find this on around about page 325. There are some slight differences to the book. The difference is I've highlighted the different values. So this is a different value, this is a different value, this is different, and this is different from the book. Now, what I'd like you to do is I'd like you to find a piece of graph paper or use a piece of graph paper in the book and plot these values on a graph. You don't have to be especially accurate with this. I want you to plot the valve and plot the flow. Now just plot the points. This is what I mean by just plot the points. Just plot the points. Don't join the line up or anything like that. Just plot the points. I've plotted both the valve and the flow on the same graph because I've managed to fit them both on. Luckily the numbers are about the same. So if you could just plot these. Now the other thing is, don't plot every single value. The table, if you look at this table, this is half of the table, and then it continues here. Don't plot every single value. If I was you, I'd plot every 5th or 6th value. So maybe plot 0, 50, 100. Plot these values in here because they're quite important. But you don't need to plot every value, just enough so that you get this rough shape. So plot every few values. What I'm going to do is I'm going to give you 15 minutes to plot this graph. Okay, so I'm going to put a timer up here. 15 minutes to plot the graph, and you let me know if you get any problems. So I'll leave the graph up there. Can everybody see the timer? Okay, so you make a start plotting a graph now. It doesn't have to be specially accurate, just roughly. Traditionally, this is done on the back of a fag packet or a napkin. And don't plot every single value, just the occasional values. You've all roughly drawn that graph and spotted in the points. Hopefully you have a graph that looks something like mine. Now, a couple of things that we do. First thing we do is that we assume that the valve opened in 0 time. So looking at the data, we got to 40 seconds, and at 40 seconds, where's my pointer? At 40 seconds, where is it? Here. At 30 seconds, the valve was at 40. And at 40 seconds, the valve was at 60. So what we assume is, at the 30-second mark, the valve opened. And it's a magical fairy dust valve that opens in 0 time. So in 0 time, it went from 40 to 60. So, here's my points dotted on. I draw a rough curve like that. And this is a rough curve. The only thing that's at all accurate is the way the valve goes straight up. At the 30-second mark, the valve goes straight up. So has everybody got a graph which looks roughly like this? Okay, good. Now, I need to find a few things. The first thing I need to find is I need to find a value called the time delay. The time delay, or TD as it's often called, the time delay is the time between when I opened the valve and when the flow started to change. So this is the first thing I'm going to try and find, is the time delay, the interval between opening the valve and the flow change. So I'll just write that down. Interval between opening valve and flow change. That's what I'm going to set out to find first, the time delay. Okay, the first thing I do is I drop a line down from where the valve opened. The valve opened at the 30-second mark, so I drop a line from there down to the time axis. What I'm hoping you'll do is follow along with me right now. All I'll do is tools, interaction, holding, pace. Okay. You should have the speed up and slow down arrows, and you can let me know how you feel if you want me to speed up or slow down. So hopefully you've all dropped a line down from the valve. Second thing we're going to do is draw a line across at roughly where the flow started. Now, I'm using lots of words like roughly and about. All of this is extremely woolly. It's all very subjective. And when we all get to calculate values, I wouldn't be at all surprised if we all calculated slightly different values. It's all down to how you draw your graph, and there's no right or wrong. So I draw a line across now, this line across, roughly where it started. Yeah, we'll talk about some of the little problems you can have with this in a moment. Now, the next stage is a little bit tricky. What we need to do now is draw what's called a gradient. And a gradient is a line that's on the main part of this line going up here is a straight line. So you kind of extend that straight line up and down. The reason we need to do this is because PID, or sorry, the Ziegler-Nichols open loop method, is a cheat. And what it expects is, it expects the value to be tickling along and then to go straight up and do that. Whereas in fact, that's very unlikely to actually happen. What actually happens is, it cuts the corner. Now, we can't deal with that corner cutting situation. So what we have to do is we have to draw this gradient, draw that gradient in. We have to draw that gradient to give us an idea of where it should have started. So we're drawing in that gradient. Technically speaking, it's to get rid of a thing called the first and second order response lag, but that's neither here nor there. How are we going with that? Everybody ready? Okay, moving right along. Now, where that gradient crossed, let's get a better arrow, where it crossed the initial value line, there, drop a line straight down. And the difference between those two lines that you've dropped down give us the time delay. Because this here, that's where the valve opened, and this here, that's where we're pretending that the flow started to change. I know the flow actually changed there, but we're pretending. Now this gives us a time delay. I reckon my time delay is around about 40. You know, rounding up. You don't have to be specially accurate here. I wouldn't be surprised if you got slightly different time delays. It's going to depend on how you drew that gradient line. It's not bad if you did. Ready to move on. Okay, forgot to put the sound on, didn't I? Let's try that again. The next thing we're going to do is to try and find a thing called the time constant. The time constant, or TC, often written as the Greek letter tau. To find the time constant, this gets a bit tricky. First thing we'll do is we'll find the final value for the flow. So we found the initial value down here, now we're going to find the final value. Now with my flow, it's still sort of tickling up, and I kind of expect it's going to tickle up and maybe drop back down again. With these sort of things, as soon as it's really stopped doing the big slopey bit, you sort of lose interest in it. So I'm going to call my final value there, mainly because in real terms, in a factory situation, I really can't be bothered sitting there for half an hour waiting for it to totally settle down. So as soon as it looks like it's going to settle down, I'm going to call it the final value. So I'm calling my final value there. And I draw a line across for my final value, and I find the distance that the process variable changed by. And that distance from the initial to the final is called y. I don't know why it's called that, it's just called y. So the change in the process variable is called y. I need you to find the change in the process variable. In my case, I make the final value about 52-ish. I make the initial value about 27-ish. So I make y equal to about, oh sorry, to change that, I make the initial value about 25-ish, so I make y about 27. You'll probably make it slightly different values, no big deal. Let us know when you're ready to go on. Okay then. Now this is the magic bit. Whatever you found y to be, you need to find 63% of that. So, in other words, I made y equals 27. I need to find 63% of 27. So 63% of 27, which is 27 times 0.63, which equals, I don't know, where's my calculator? Right, in my case, that equals 17 odd. So, what you now need to do is from the initial line, go upwards 63% of your y. So in my case, my y was 27, so I go up 17. Yours might be different, that's fine. So if your y is 27, you go up 17. If your y is something different, you go up a different number. So you go up, from the initial value, you go upwards 63% of the final value. You see, because the time constant is the, let's do a definition. Time constant is the time taken to reach 63% of final value. So I want to find how long it took to reach 63% of its final value. So I find the difference it made, I find 63% of that difference. So difference it made is y. Started there, ended there. I find 63% of that distance, and I draw a line straight across. And that, where that intercepts the original curve, so let us know when you're ready to go on. Right, where that intercepts the original curve, I drop a line straight down. Now, from where the flow started to change, or at least where I'm pretending the flow started to change, which is that point there, to the time it took to reach 63% of its final value. Now, I reckon that's about 50 on mine. Once again, yours might be slightly different. No big deal. So, once again, let us know when you're ready. Last thing to find. Now we've found TD. So we've got the time delay, we've got the time constant. Now we need to find a thing called the open loop gain. It's open loop because we've got the thing in manual. So what we did right at the beginning was we put the loop into manual with the valve at 40%. And then we manually entered a new valve position, this time 60%. So it's open loop. The whole system is in manual. I'm going to find the open loop gain. And the open loop gain is, so K equals the change in process variable divided by the change in valve. So let's have a look at this. In my case, I made the change in the process variable, that's the y value. So that's actually going to be y over what I call delta valve position. Now my y value, I might choose a different color, my y value is, I made it roughly 27, and my valve went from 40% open here to 60% open there. So my valve changed by 20%. So I make that 27 divided by 20. And that comes out as, calculator, 27 over 20, 1.35. So you calculate your open loop gains and let us know when I can. I think that was everybody. Is anybody still working? I'm happy to wait. Is anybody still working, or shall we move on? Okay, that's everybody then. Right. So now I've calculated these three things. I've calculated my TD, I've calculated my TC, and I've calculated my K. Now, I go to this table. This is a standard table. You'll find it in any reference manual to do with instrumentation. It's how you calculate the different things. First thing we're going to decide is, are we going to use pure proportional control? This is pure proportional. Are we going to use P and I control? In other words, proportional with little nudges. And are we going to use P, I, and D control? The decision we make is this a totally and absolutely predictable system where we're going to use pure proportional? Is it a system that's pretty predictable, but not totally predictable, in which case we'll use P and I? Or is it a completely inherently unstable system where we have to use P, I, and D? Now, if you can remember back to what I said at the beginning, what is the one that we use 99.9% of the time? Right, PI. And you know what? A lot of PLCs don't even give you a D term because nobody ever uses it. So we're going to use PI. We're going to use this row on the table. And to calculate the P, we're going to use this equation. This equation gives you the P value. That's going to give you the P. The I value we're going to get from, oh, that's not very good car, is it? Let's try it. Oh, that's not too good either. But anyway, the I value, let's try the green. That's what we're going to use to get the I value. So those are the two equations that we're going to use to calculate the P value, and that's a gain, and calculate the I value, which it tells us is an integral time. So, using those equations, here's the values I found. I found my open loop gain, K, to be 1.35. That's not good, guy. Open loop gain. I found my time delay to be roughly 40. And I found my time constant to be roughly 50. Now you may have found the same values. I'd be surprised if you did. Okay, so I'm going to calculate the go back. There we go. First thing I'm going to calculate is the P value. From the table, the equation I use is that the P value is 0.9 times TC divided by K times TD. So in my case it's 0.9 times 50 divided by 1.35 times 40. So I make that 45 over 54, which is roughly 0.8. I'll give you a moment to do your calculations and let us know when you're ready to move on. Okay, well, I make that time to move on then. Now the I term, I'm going to do the calculation for the I term now. So from the equation, from the table, the equation said Ti, which is integral time, is 3.33 times the time delay. In my case, the time delay was 40, so 3 1/3 times 40. I make it 133.2. I'll give you a moment to do your own calculations and stick your hand up when you're ready. Alright, time to move on then. So, I'll just put up a blank page. I end up with a P of 0.8. P, oh, that's a terrible colour. P, 0.8. And an I of 133.2. Okay, they're the values I ended up with. What I'd like you all to do is post the values that you got. I've actually got the sound off at the minute, Eddie. What I'm waiting for is if you could post me your P and I values. Okay. Now, the reason I did that wasn't so that I could say, oh yeah, you're right or you're wrong or anything like that, but to say they're all right. They're all going to work. You've got two boxes in your PLC, and I could almost guarantee to you that if you put any of these numbers in those two boxes, it will control. In some circumstances, the control might be just a little bit over-enthusiastic, tendency to oscillate. In other circumstances, the control might be just a little bit under-enthusiastic. It takes a long time to get to set point. But in all cases, I bet this is going to work. These numbers will work. Now, if you put these numbers in and you find that it's a bit over-enthusiastic, it's oscillating, all you do is just halve whatever you found as your P term. If you stick these numbers in and you find it's just a little bit slow, you just double your P term. What that means is, if you've got, although I calculated this to be 0.8, it could easily be 0.4. And it could just as easily be 1.6. In actual fact, the values that we calculate using the open loop bump method, they're just a starting point. And what we're supposed to do is we're supposed to use those just as an indicator so that we know roughly where the P term really is. If you've calculated your P term to be roughly 1, then you know that it's somewhere between 0.2 and 4. It's somewhere between there. So you've really narrowed it down a lot, because when you think that the P term can be anything between 0.01 and probably about 32.76.7, then you've really narrowed that range. You've said, oh, it's 1-ish, so it's going to be somewhere between 0.2 and say 4, maybe 8, you know? And you might say, well, there's a massive gap between 0.2 and 4. Well, there isn't. Not when you're doubling it and halving it each time. To go from 0.2 to 4 is only a few steps in doubles. Similarly with the I term, I'm making mine around about 130. That tells me it's somewhere between, say, 50 and 300. Maybe bigger than that. And once again, I've really, really narrowed that range down a lot. With the I term, if when you're watching it, it's just constantly sitting there, so there's the set point, and the flow is just sitting below set point and not getting there, then you know you need to give it a bit more, because the I term gives it those little nudges which get you to set point. You want to increase the nudging rate, which means you want to make it a bit smaller, because it's a time, so you make it smaller to make it more enthusiastic. If on the other hand you find that the flow has done, let's pick a good colour, the flow has done this and it's settled down, but it's constantly just hunting, you may find that that might be because your I term is just a bit too big. So, just a bit too small. So you have to make your I term just a little bit bigger. If you find that the valve is always creeping, and you look at the valve, and the valve's going, say, 57, 60, 57, 60, 57, 60, then you've got to say, well, it's doing too much nudging. So I might back that off a little bit. And to back off a time, you make it slightly bigger. So you double it. So these values that we calculate, they just give us a starting point. And you take it from there. Okay, so that's the open loop bump method. It's a little bit involved. It's itemized in the book. And like I say, once you've done a few hundred of them, you can kind of do them without thinking much. There can be lots of problems with the open loop bump method, especially if we have a very fast loop. If we have a very fast loop and I bump the valve there, and the flow just goes dunk like that, well, I can't get anything off the graph, because to all intents and purposes the flow immediately changed. If that happens, well, you cheat. You just say, okay, fine, it all happened too quickly. I'm going to say the time delay was half a second and the time constant was half a second. I can still calculate the open loop gain, which is the important one, by working out the change in the valve and the change in the process variable, because the open loop gain is still the change in process variable divided by the change in the valve position. So I can still calculate that, and that'll give me halfway decent numbers. Another problem you may find is, especially with tanks. With a tank, it's unlikely that you're going to start at a stable situation. Tank level, you put the thing in manual, and the tank level will probably either creep up or creep down. You then make your bump, and so I'll just draw my valve. There, dunk. There's where I made my bump. So you make your bump, and you'll see the tank level increase. and then it's unlikely that the tank level will stabilize out again. It will probably continue increasing. So what we do is we say, okay, what I'm going to do is I'm going to pretend. I'm going to pretend that here where I made my bump, that's where I'm really interested. I'm going to pretend that that was level across there. And I reckon it finished doing all of its control move stuff around about there-ish. So I'm going to pretend that that's the initial value, and this is the final value. And so my y is the distance between those two. Now, you might say, well, hang on, this is all pretending. Yeah, it is. It is all pretending. But what happens is, the further you go down this way, the bigger the y value becomes. And the bigger the y value becomes, because k equals y divided by the change in valve position, the further you go down that line, the bigger the k value becomes. Now, the further you go along that line, the bigger the time constant becomes. So the further you go down there, the y value gets bigger, the k gets bigger, and the time constant gets bigger. But when you look at the equations going back here, the equation is 0.9 times Tc divided by k times Td. So going back to this equation, P equals 0.9 times Tc divided by k times Td. What this means is, if you go further down this line, the k value gets bigger, but so does the Tc value get bigger. So the two pretty well cancel each other out. And so it doesn't matter if you're not particularly accurate in choosing the bit that you call your final value. It's all very woolly, it's all very wishy, this stuff. It's not scientific.